Okay, welcome, Chem 1 students from Destiny High School. I know it's been a while since I posted it. I personally posted a video. I've been using Khan Academy and other sources because they were already done. Just been getting kind of lazy on it a little bit, maybe. Um, been having a hard time staying motivated teaching like this, not seeing you face to face. So, wanted to go through. This is actually homework 12 in Chem 101, your questions and problems may be a little bit out of order or a different order. They may be phrased a little bit differently, but it's going to cover the same topic. So I wanted to go through a few of these. I'm not really going to answer the questions, but I'm going to talk about certain questions and what you need to know for that. So this question one says, which of the following phase changes represents sublimation? So um, I'm just going to go ahead and do this. So we have three main phases that we deal with in chemistry: solid, liquid, and gas. Those are our three main phases. Well, to go from solid to liquid, we melt. All right, to go from liquid to solid, we freeze. All right, to go from a liquid to gas, we boil, or another word to say there is vaporize. So call it vaporization. Sometimes you call it evaporation, but that's only if it happens without a temperature change. And then the other thing that we can do is if we go back from a gas to a liquid, it condenses. All right. Now, so we can make this jump from gas to solid, and that would be deposition. Or you can also go from a solid, erase that one. Or if we go from a solid directly to a gas, that is sublimation. All right. So using that information, you should be able to answer that question: which of the following changes represents sublimation? With sublimation, we're looking at solid to gas. All right. What intermolecular forces are present between two molecules of HBr? Well, first thing we need to know is what are the three types. So the intermolecular forces that we primarily deal with are London dispersion, which are all molecules. All molecules have London dispersion. All right, so going through these, I already talked about London dispersion a little bit, but London dispersion, all molecules experience London dispersion. So you will always have London dispersion forces. These are the weakest of the three intermolecular forces. Now, real quick, intermolecular forces are dealing with, so in this case, we have HBr, and we're talking about how is HBr going to interact with another molecule of HBr. So we're not talking about the bond right here. We're not talking about this bond. We are actually talking about the interaction or the force that would hold two separate molecules together. So we're looking at this in between. This is not a chemical bond. This is a physical bond. So all three of these are physical bonds, not chemical bonds. So London dispersion are always present. Typically, London dispersion, if if it is a nonpolar molecule, if both of them are nonpolar, it's the only force. It's the only force present in nonpolar. All right. But if the molecule is polar, it can have dipole-dipole and or hydrogen bonding if it meets certain requirements. So dipole-dipole is dealing with polar molecules. So a polar molecule can have London dispersion as well as dipole-dipole. Now, what I'll tell you about this one is that bromine is a larger molecule. Remember that the bromine is going to have these 6 electrons around it. So it's going to have 3 lone pairs around it. Bromine is also more electronegative than hydrogen, so it's going to have a slight dipole facing that way, meaning the hydrogen is going to be partially positive and the bromine is going to be partially negative. So that means this end of the bromine will be attracted to this end of the other hydrogen bromine molecule, because this one has that dipole facing that way. So you always have this positive side and a negative side, and they line up as such. All right. So far, this molecule is a polar molecule, and typically, whenever you have a binary molecule with 2 different elements, they're always going to be polar. So just kind of know that. Now, looking at this, it's a polar bond. Now, before we decide which ones are going to be there, we have to decide one more thing. So we also have to look at what's present in the bond. So for hydrogen bonding to occur, only molecules with nitrogen, oxygen, or fluorine chemically bonded to the hydrogen, and they interact with a similar molecule. So we do have a hydrogen, but we don't have nitrogen, oxygen, or fluorine. So it is definitely not that. So for this one, we're experiencing dipole-dipole and London dispersion. D would probably be the best answer on that one. All right, moving forward. So approaching this question, what intermolecular forces are present between 2 molecules of CH3, CH2, SH? So I'm going to go ahead and draw this one just so you can kind of see what we have here. The CH3 looks like this, and then we have a CH2. These are a lot more complicated molecules than what we were drawing before. All right, now remember that sulfur is going to need to have its 8 electrons around it. So one of sulfurs is going to be combined here to this hydrogen, and one of them is going to be combined to that one. We have to have the octet around there. So now notice that this part, everything's kind of the same around it. So this side of the molecule would be nonpolar, whereas this side of the molecule has this little bent structure. So right here would be a bent structure, and that makes it going to be polar. And so we're going to have this partial negative on this side and partial positive over here. So we do get this kind of a polar thing in this general direction on it. So remember that all molecules have London dispersion. And then if it's polar, we need to look for it to be hydrogen bonding. We need to have nitrogen, oxygen, or fluorine present. So those are not present. So we know it's not that, and we know it's not dispersion only because it is polar and nonpolar, and all molecules have London dispersion. So again, it's going to be out of those. All right, moving forward. What intermolecular forces are present between 2 molecules of CH3, CHF? So if I had CH3 again, drawing this structure, CF3. Now, I'm not going to tell you on this one, but you have to decide. So one of the things that I notice immediately is I have hydrogens on this side and fluorines on this side. I also know that fluorines are going to have 6 electrons around it, whereas the hydrogens won't. The other thing is I know that fluorine is highly electronegative, meaning it's going to attract more electrons than anything else in this molecule. So the question you have to ask is this molecule polar? Polar or nonpolar? If it is polar, then it could have dipole-dipole. If it is nonpolar, then it can only have London dispersion. Everything will have London dispersion, but if it's a nonpolar molecule, it can only have that. The other question is hydrogen bonding possible? And so I'm going to address this real quick. It does meet the requirements of having both fluorine and hydrogen, but are the fluorines and hydrogens directly connected? And so the answer is fluorine's connected to carbon here, hydrogen is connected to carbon. So hydrogen bonding in this case is not possible because the fluorine and hydrogen aren't connected directly. So you can go ahead, should be able to answer that question on your own from that piece of information. Number 5, what intermolecular forces are present between two molecules of CH3OH? I'm going to go ahead and draw this and then I'll talk about it. All right, so again, we have to ask the same questions. Is this polar? Or nonpolar? That's going to be the first thing. Well, looking at it, for being nonpolar, we need everything to be the same all the way around it. So the answer to the first question, is it polar or nonpolar? This is a polar molecule, and it's because this one oxygen makes everything different. All right, so that is going to give us a polar situation here. The next question is do we have oxygen and hydrogen? Do we have opportunity for hydrogen bonding? And remember, if we have oxygen, nitrogen, or fluorine directly bonded or chemically bonded to a hydrogen, we have that opportunity. So yes, we do have that situation right here. So now, if it was attached to another molecule of this, there is potential for the O of one molecule to be attracted to this H and the H of the other one there. So there is potential for hydrogen bonding there. And so, again, that comes into the question of what options do you have? The strongest one is always going to be what's going on there. So let me pull us to the side for this one real quick, and I'm going to pull up this question on Chem 101. So give me a second real quick. All right, so I'm going to go ahead and kind of address this and see if I can get rid of this screen real quick. While it does meet some of the criteria here with this hydrogen and oxygen connected, it doesn't meet all the criteria. You see how this is kind of trapped in the center here? This is going to prevent it from performing hydrogen bonding. While it does have a dipole right there, the dipole is going to happen on the oxygen, and it's going to be real hard for it to connect directly to another hydrogen like that. So this one specifically would be dispersion and dipole-dipole. mainly because of the position. If the molecule looked more like this, and I'm not going to draw all the hydrogens, I'm just going to draw lines for the hydrogen, and then we saw COH on this end, then where it's out there on the end, then it would be likely to form hydrogen bonding. But since it's kind of trapped in here in the middle, that's going to make that molecule hard to have that particular thing. All right, moving on. Number 6, which of the following represents the intermolecular forces in CO2? Now, if you remember from last unit, CO2 is drawn like this. And what I'll tell you about this molecule is it's completely symmetrical. So that means it is nonpolar. So since this is a nonpolar molecule, which force or forces can it have? All right, going in here, predict the lowest boiling point. All right, so I'm going to pause this one, and I'm going to start part 2 at this part because I only want to deal with one part at a time. So I'm going to go back to these questions 1 through 6, dealing with intermolecular forces, the 3 types, and dealing with polarity to some degree, and dealing with boiling point and freezing point and sublimation and those type of questions. So just kind of keep that in mind. So questions 1 through 6, what are the things that drive those?